So everyone, welcome. I have no idea how many's here, but so I'm probably going to be. I said this in my last talk too, but we got 15 in the meeting, so it's hard for me to see my slide preview and to see the chat room at the same time. So if you've got questions, just unmute yourself and go ahead and ask them. That's perfectly fine, and feel free to interrupt me. If you like. I mean, it makes it more interactive for me, and so I know I'm talking to humans and not a screen, and it'll get you a fast answer to your question. So feel free. If you're not comfortable with that, I will try to check chat periodically, and if someone else sees something in chat and I missed it and wants to speak on their behalf, please do that as well. So, but yeah, let's kick this talk off. So welcome to my talk, Dungeons, Dragons, and Graph Databases. My name is Ghe Royse. I'm a developer advocate at Redis Labs, which means that a significant part of my job is going out to events like this and giving talks. It's not really going out as much as it used to be. It's sitting in the same room I sit in every day, but talking to a bunch of people in an area. So it's still good. I'm looking forward to the day when we can all do this in person again. And a live audience is just, I think it's more fun to be part of a live audience, and it's more fun to speak to a live audience. So hopefully soon, maybe this fall. So, but anyhow, this is my big cover slide. But give me a follow on Twitter, please. But the thing that's really useful here is the GitHub URL, github.com/GheRoyse. I've got all my code out there for this talk and all my other talks. There's links to the slides for this as well there. The link to the slides is broken. I'm going to fix that as soon as I'm done giving this talk. So I just discovered that today. So, but I'm a developer advocate. I've been writing software for years and years, but I'm also a big fan of the Dungeons and Dragons. And so I thought it would be worthwhile to share my character sheet as well. So this is my character sheet. I like to play Dwarven Bards, 5th level Dwarven Bard. I thought neutral good was a good alignment for me. It's like, well, I'm on board with the civilization thing, but I'm also, I'm not pure chaos either. Neutral good. That feels right. A strength 10. I'm kind of average there. I'm fat, so I'm kind of slow, so I got a low dex. But I'm a little harder than you might think. I'm not terribly smart or wise with 8s in both of those, but my charisma of 16 makes it look like I am. So that'll give you some context for this talk. As the D&D player, I've got a problem, and that problem is that I need to figure out how to maximize my character experience in the dungeon. I need to hit all the rooms. I need to find the rooms that have the best monsters so that I can get the maximum XP. And I need to find the rooms that have the best gold so that I can get the gold to buy the gear to allow me to defeat more powerful monsters, to get more levels, and the cycle repeats. That's my problem. And, I'm a gamer, but I'm also a software developer. I've been writing software for about 25 years. And so I could solve this problem with technology. Like I could build a database representing the dungeon and then query that database and find the answers to these questions, find the best paths through the dungeon, find the rooms with the best monsters with the best gold. And so I thought, well, I could do that using a relational database with the rows and the columns and the ones and the manys and the inner and outer joins and all that stuff. Or I could do it with a graph database with all the nodes and the relationships and the labels and the properties. And you're probably, and I'm kind of assuming that the audience is familiar with relational databases. SQL is the only programming language that I learned in college that I'm still using to this day. Most of them have gone to the wayside. Not writing a lot of COBOL code anymore. Not writing a lot of even a lot of C or C++ anymore, honestly. But I still occasionally have to use SQL to query relational databases because there's a lot of them out there. So I'm assuming that everyone's had a similar experience. Even newer developers have probably used a relational database. Even in a boot camp, you've probably touched them. So that's an assumption I have. If you haven't used a relational database, the graph stuff's still good. It's just the contrast won't be quite as valuable. The contrasting aspect of it may not be as valuable for you. And so I'm going to build a model of a dungeon using a relational database. I'm going to build a model of a dungeon using a graph database. And then I'm going to use that comparison to teach what graph is. So, and that brings up the question, what is a graph database? And that's the right question, but there's a question under it. And that's the question is, what's a graph? So if you're like me and you don't have a heavy math background, I had to go out and learn all this stuff from just sort of trial and error and reading blog posts and books and talking to my wife, who actually has a math degree. And a graph is a set of nodes or vertices that are connected by relationships and edges. A node is, in essence, a point or a vertex. This is I-20 is a graph. The point on the tip of it, and I've got one here physically that I'm pointing at as well, is the vertex. That's the point. And the edge is, well, it's the edge, right? It's the thing that connects the points, that connects the vertices. And that's a graph. Now, this isn't actually a graph. I'm not holding a graph in my hand. A graph is a representation of the structure of this thing, right? It's a representation of the nodes, the vertices, and the edges that connect them. It's a mathematical representation. Other things can be graphs, not just 20-sided dies, not just platonic solids. Networks, like network topology, like the internet, is got a bunch of nodes connected via pieces of wire or wireless even. That represents that can be thought of as a graph. Roads, the roads of a city or of a nation or of the world can be thought of as graphs. They've got intersections where the stoplights are at. You've got the nodes connecting them, which are the roads themselves. Graphs are just abstractions around these ideas, mathematical abstractions. The simplest graph is the null graph. It's a graph that has nothing in it. There are no nodes. There are no relationships. Just nothing. There's, I think, some debate among mathematicians whether this is truly a graph or not. It's kind of like asking if null is truly a data type or not. But yeah, we still need to deal with null. It's a thing that, in practical terms, exists. The null graph is a graph with no vertices, no nodes. So, but they're not very interesting. So let's add some nodes. And so here now we have a graph full of nodes. They're just points in space. There's no relationships between these nodes yet. There's no edges. But the nodes are out there and they exist. And so this is a valid graph as well, just like the null graph is. But it doesn't really start getting interesting until we start relating the nodes in the graph. And so here we'll add some relationships. And now we're starting to see things that look like what people think of when they think of a graph. You got nodes, they've got connections, and we can think about them as graphs. There's some terminology around these types of graphs. So we had the null graph. We had the graph without any relationships. I don't know that there's a word for that specifically. But when you have portions of the graph that aren't connected to each other, they're referred to as isolated. So node E isn't connected to anything, and so it's isolated. Nodes B and F, while connected to each other, aren't connected to anything else, and so they're isolated. And actually, even the big set of nodes in the middle, the 4 nodes that are all connected together, even they are isolated from the other portions of the graph. And so you've got these partially connected graphs where they have isolated sections, like isolates, I guess you could call them. If you connect all the nodes, then the graph is no longer isolated, or the subgraph is no longer isolated. In fact, the entire graph is referred to as being connected. And this means that every node has a path to any other node, but it might be by way of an intermediate node. So node D and node G in this graph have a path via A and C that connect them. And so D and G aren't directly connected, but they have a path that connects them. So this is referred to as a connected graph. There are no isolated pieces. I don't have a picture of it, but you can also create fully connected graphs. And this is where every node is connected to every node directly. So that means A is connected to nodes B through G. And B is connected to the nodes C through G and A. And you've seen pictures of these. It's often used to represent what the internet looks like. You end up with a circle of nodes and lines that connect them all together. So that's a connected graph. Another thing about this graph here is that it's undirected. So A to B and B to A, the relationship is the same. There's no extra information in that relationship. It's just the A and B are connected. But you can make graphs that are directed where there's a directionality to them. that shows the nature of the relationship. If this graph represented, say, a mother-child relationship, then that has a directionality. The mother and the child are related to each other; they're connected, but there is a natural direction where the mother beget the child, and so that's an extra bit of information. Graphs that have this directionality are called directed graphs. Graphs that don't are called undirected graphs. And the nodes of the graph can be described in terms of their relationships with degrees. This isn't like degrees of in a circle. This is degrees as in how many connections in or out it has. So node A has 3 relationships, 3 connections, and so it has a degree of 3. Node E only has 1 relationship, so it has a degree of 1. You can also talk in terms of out degree and in degree, where out degree is the number of outgoing relationships and in degree is the number of incoming relationships. And so in degree, out degree, and degree. And I've made sort of a nice, neat, tidy little graph here where it fits on a nice 2-dimensional piece of paper. But there's actually not any rules that say that has to be so. Anything can connect to anything. And so a node can connect to itself. Nodes can connect mutually to each other. Nodes can connect to the same node multiple times. No rules. Anything goes. And so that's sort of like a graph theory at a really high level, enough to understand graph databases in 5 minutes. So a graph database is when we take this structure and we lay data over top of it. So now these nodes aren't just letters, they're actually the rooms and the treasure and the monsters in our dungeon. And those nodes can have data added to them in addition to having labels. So that room has an ID and a name. Room 1 in the dungeon is the statue room. Every good dungeon has a statue room at the beginning. You walk in and there's a statue, and you have 2 different paths you can take. The monsters have a name, they have a challenge rating, and they have an experience point value. The treasures have a name and a gold piece value, and they all have IDs. And we also can put data on the relationships, giving them a type. So the room contains a monster, the room leads to another room, the room contains treasure. And all of that really creates a very intuitive representation of our dungeon. Our dungeon is a series of rooms that are connected via corridors, and they contain things. And so this graph very intuitively represents that. On nodes and relationships, a node represents items. They can have labels and attributes. Label is room, an attribute would be the name. I tend to think of the nodes as nouns. They tend to be the nouns of the system. And nodes don't need to have relationships. A node can just be out there hanging out by itself with its data. Relationships are connections between 2 nodes, and they cannot exist without these nodes. If the nodes go away, the relationship goes away. It's like I like to think that the nodes are 1-dimensional and the line are 0-dimensional, and the relationships are 1-dimensional. And you need 2 points to determine a line, and if you don't have those 2 points, then the line's gone. You just have the point now. And so that's sort of how I think of the graph structure. But what it means is if you have a room that leads to a room and you delete the first room, that connection goes away as well, which makes sense. Relationships have a direction, and they can have attributes as well. And so like leads to, you can maybe give a distance of how many feet it is down that corridor in a dungeon. I found that when I want to put attributes on my relationships, it usually means that I've got a node that I'm thinking of as a relationship. And so I tend not to do that, but that's not a hard and fast rule. That's just sort of an observation I've made over the years. Well, over the year and a half of messing with graph databases. And I think they read like sentences. Like if you're doing it well, it should read like a nice sentence with a transitive verb, where the room contains a monster. You got the room that's the subject, the monster is the direct object, and the contains is the verb that links them together. So the room contains a monster. It also means you could flip the directionality and say it the other way and say the monster is contained by a room. But then you're using the passive voice. And well, my English teacher told me that was a bad idea. So I'm not going to do that in my graph databases. So that's sort of the theory behind graph and the theory behind a graph database. But how's this actually look for real? Like, you know, we got some concepts in our head, but how are we going to turn this into like a real thing that we can play with? What's this look like in my code? Well, because we still got the problem, right? I still need to find the rooms that have the monsters and the treasure. And I still have to decide if I want to solve it using a relational database or if I want to solve it using a graph database. Spoilers, we're going to use a graph database. And so the first thing is, well, what kind of query language do we use to talk to these things? Now, if you've done relational databases, you know that SQL is the lingua franca of talking to relational databases. You select things, you from tables, joining with where statements. You can insert and create and delete and update all to your heart's content using SQL. And I'm assuming that we know SQL. But you probably don't know what language you'd use to talk to a graph database. Well, the language we're going to use, and it's an open one that Redis Graph uses. Neo4j actually created this language to work with their graph database. And we're implementing it for Redis Graph, is a cipher. Cipher uses a series of match statements and then can return pieces of that. The match statements are kind of like, well, let's look at the next slide. This is a better one. When we match things, we create these matching patterns. And the patterns that we match on for Cipher kind of look like a cross between ASCII art and like regular expressions or something, or like a query language. And so this particular one matches the relationship of a room containing a monster. And so the first node matches a room node, a room with a label, a node with the label of room, and assigns it to a little variable called R for use later in our query. The colon monster matches something with a label of monster and assigns it to variable M. And this matches the relationship. And you can see that the parentheses are round, like we're drawing the nodes, you know, when we draw a graph on a piece of paper. You know, they got the parentheses that make them sort of round. They look like it. They look like them. And the contains is a little square. It uses square brackets, and it's got a right here. It's got that little greater than that shows the arrow. It's you're drawing a little ASCII art arrow showing the directionality of that relationship. And these matches will go through the entire graph and find every pattern that matches, every place that matches that pattern. So every room that contains a monster. If a room contains multiple monsters, that room and its monster will be returned multiple times. If that monster's in multiple rooms, which doesn't make sense as a dungeon, but the graph can completely do it, then that monster will be duplicated. So, good so far. Let me check to see if there's any questions yet. Yeah, that's right. Yeah, I should go back to my COBOL days, shouldn't I? Sorry, I just saw the question about COBOL in there, the comment about COBOL there. So, so let's compare and contrast these. Let's do create, read, update, and delete, the 4 classic CRUD operations for databases. Let's show them in SQL. We'll show them in Graph. And what we're going to see is they're not super different. So here's our insert statement: insert into rooms, the columns we care about, and the values we want to give them. So here we're creating a statue room. To do this with Graph, we need to create a node. So we use the create command. And then we create a node, and we give that node a label of room. So r:room. Technically, the smallest thing we need to do there is we could do create r, and we wouldn't have to give it a label. I don't think so anyhow. I haven't tried that. I may be wrong about that. Unlabeled nodes I haven't really found to be particularly useful. So I always label them. So we create a node of type with a label of room, and then we assign it to R, and then we use that R variable to set properties on it. And then we set the ID and we set the name. Now, one important difference here is that in the relational database, we have predefined columns. We have created a table that has these 2 columns in it. In the graph, there are no tables. We're creating a node and we're just giving it properties, and we could give it any property we want. We could have them. We can treat them kind of like documents in a document database, where the properties are whatever makes sense for the particular node. And so we could have r.id equals 1, r.name equals statue room, and r.trapped equals true. So maybe that statue's trapped. So that's how we create nodes. To read nodes, to read a room from the database, here we use the select statement in SQL. Select columns we care about from the table we care about, where column equals value. This will give us the statue room. For a graph query, we use our match, and we're saying match a node that has a label of room and assign it to R. And then we say where the ID r.id is 1. So we're filtering out. So match the entire graph for every node that has a label of room. If there's 20 of them, it'll return 20. If there's 1, it'll return 1. If there's none, it returns none. Then filter so that we get just the one we care about, and then return it. And then that will return that node for us to look at. To update rooms, in SQL, we say update room, set the name to the statue hall. It's getting an upgrade. It's got multiple statues in it now. So it's not just a statue room, it's a statue hall. It's lined with statues on both sides. May or may not be trapped. May or may not be petrified adventurers. But we update the room, set the name to statue hall, where the ID is 1. Make sure that where is in there, or you've updated every room in the dungeon to the statue hall. For graph, the first 2 lines are identical because we're trying to find things in the graph. We want to find all the rooms. And then we want to find the rooms with an ID of 1, which is our statue room. Once we have that, then we can set properties on it, just like we did before. This allows us to change properties, or we can add new properties. But it's that match where is exactly the same as in reading, and it's actually the case for deleting as well. If we want to delete from SQL, we say delete from rooms where ID equals 1. Again, make sure you get that where clause, or someone's going to hate you because you will have deleted the entire dungeon, and then we won't have a fun game to play. For graph, again, it's match where room where ID. Match room where ID is 1, and that gives us all of our rooms. It gives us, well, the match gives us all our rooms, the where gives us a specific room, and instead of returning it or setting it, we're going to delete it this time. We want to delete that room instead, and that will delete the statue room. So this is your basic create, read, update, delete for nodes and records in graph and relational. Now I've used a particular syntax, and I want to point out that there's an alternative syntax you can use. I've been using this syntax where I say match a room where the room ID is 1. But you don't actually have to use a where clause. You can actually use curly braces in the matcher and say that has property that matches this. You get these curly braces, and then it's ID colon 1, and then you could do like comma name colon and then in quotes statue room. And it looks just like a JavaScript object. In the curly braces there. And so that creates a more sophisticated match where we can go out and do it in a single line. These are effectively the same thing. It's just a variant syntax. And I've got a couple scenarios where I've used both. Yeah, question.
So when you are you're creating this node, I'm just trying to kind of wrap my head around. Because you're using Cypher, it just automatically knows, like, okay, we're doing graph database, so this new object is a node, and I'm assigning it to this R variable.
Yeah. So the create statement, I'll go ahead and jump back. There we go. For create, so the R colon room means create a node and give it a label of room. So the create command actually is what creates the thing. And so that's an instruction to a graph database that understands Cypher to create a node.
Okay. So it's telling the database to do that. Okay.
Yep. No.
So can I ask, is that like saying that's the type of node it is? There's only one? Is there only one type that you're allowed for?
So they call them labels, and
Right.
actually the reason we call them labels is because nodes can have more than one label. So it could be both a room and say a chamber,
Okay.
or it could be a corridor or a hallway. Maybe those are different in your game for some reason. And I suppose you could almost do there's a natural sort of OO thing you want to do there, where you want to start thinking about in terms of inheritance. It's like, well, this is a NPC, but it's also a monster.
Yeah. Yeah.
Or, and so it's like, and that could make sense, right? You might want to query all the animate entities in your dungeon, the monsters, whether they're NPCs or monsters or player characters. Those would all be things, right? And so you can see ways that these labels could get really, really interesting and useful.
You could say like create a node with the label room is like creating a new room. That's the same thing.
Yeah.
Okay. That just helps it make more sense in my mind for some reason.
Well, we're going to go ahead and run some real queries here in a bit. So hopefully that will help solidify it for you too. But I think it's cool because it's a different way of thinking about data than I've done before. And I actually think the graph structure is, it's more intuitive than a relational database because it can map directly to your problem domain. If you're thinking about like a transportation network, well, if you're thinking about a dungeon, right? A dungeon is literally made up of a bunch of connected rooms that have things in them. And so it's the database structure is directly mimicking the object graph that you would have in memory for, you got all your objects in memory, and it's how you as a human think about the problem. And so I find that it's actually really intuitive to work with. So, yeah, and so this match here, you could also do a create this way. You say create a room with properties automatically. You don't have to use the set. You can use that same syntax, which is this right here. So I can say create a room with an ID of 1 and a name of statue. You'll notice in this particular example, I didn't put the R in front of it. And that's because I don't need to reference it, because I'm not using a set command later. So that's another way to do that. So you can create rooms that are and then set properties on them, or you can create a room with the properties already in the matcher. So let's look at creating monsters. It's pretty much the same process. So you insert it into the monster table, and here we're creating a monster, and I'm using that newer syntax, or the alternate syntax where I'm using the curly braces to define all the properties. And then here I'm creating a treasure, and I'm actually mixing them. Like I'm creating a treasure and assigning it to T. I give it an ID and a gold piece value, but then I use the set to set a value on it. So you can mix and match those as well. And so here's what our relational database looks like so far. We've got 3 tables that are unrelated to each other. We've got a list of rooms, a list of treasures, and a list of monsters. And here's our graph database so far. You've got 7 nodes sitting out there in the ether. Some are rooms, some are monsters, some are treasures. And we could query these easily and say, give me a list of rooms, or give me a list of treasures, or give me a list of monsters. But it just gets interesting is when we want to start putting a monster in a room or putting treasure in a room. So to put a monster in a room with a relational database with SQL, the first thing we have to do is alter our table. So, as our software is growing here, we're going to have to, part of our process is going to be monsters now need to be added. The table needs to be modified to add a foreign key to the room table. Then we can add a record, and we can update those records to say, set the room ID to 1 for monster number 4. Put Alice the elf in the statue room. Put Bob the ogre in the armory. And so we alter the table and we do an update. For graph, we don't have to alter any structure because there is no schema. It's just whatever we want to put on the nodes and whatever relationships we want to create. And so it's simply a matter of matching the 2 nodes that we want to connect. And so we'll match a room with an ID of 1. And so that we'll walk the whole graph, look for all the rooms, find the one that has an ID of 1. And we'll match for a monster with an ID of 4. That'll walk the graph, find all the monsters with an ID of 4. Should be one of them. And now we've assigned those to R and M. and we can create a relationship between them by creating a contains relationship. And so now they're related. Now the monster contains a room, or the room contains a monster. And that's it. That's all we have to do. So you just match the two things you want to relate and then put the relationship between them.
So is that, guys, is that contains like a keyword, or is that just you're naming a relationship?
That's just the name of a relationship.
Gotcha.
It's
Thank you.
So nodes have labels and they can have multiple. Relationships have types and they have one. And a relationship has to have a type.
Gotcha.
So there is a temptation to use this syntax to create the contains relationship. Whereas, like, can I just do this all as one big create statement? I did this when I first started getting into this. I made this mistake, and so I always share it with everyone. This doesn't do what you think it does. These create new nodes because it's in the create command. And now we've got two nodes with an ID of 1 and two nodes with an ID of 4. And then it relates the newly created nodes, leaving the old nodes unrelated. So that doesn't work. You have to match the things before you create the relationship between them. So just a little caveat on that. Putting treasure in a room, it's the same process. Alter the table. Put the +1.
I have a question about that previous slide. So can't you make the IDs primary key? Like there's only one monster with ID 4.
So there really aren't primary keys. There aren't keys in that sense. Nodes do have, with Redis graph in particular, has sort of an intrinsic ID, which is just sort of the number of the node, and each node has a unique number. It's kind of like having a GUID, but it's just an incrementing number. But you can't use the curly brace syntax to match on it. You have to use a where clause because you need a special function to access it. And so the ID being used here is just another property. I'm saying it's an ID out of convention, but it's not actually indexed or anything like that.
Okay.
Which is why it can be duplicated.
Okay, sounds good. Well, makes sense.
And so here we are updating the treasure room. The treasure in the room is the same thing. And putting a treasure in a room is, of course, exactly the same pattern. Match the room, match the treasure, create the relationship. So now our relational database looks a little more like something we've probably used in our careers. We've got a room that has a one-to-many relationship with treasures and monsters. And so the monsters and the treasures are in their respective rooms. Our graph database is now has relationships as well, but each room is isolated. The room and its contents are isolated from each other. But even with this this structure, we can do some interesting queries, both relationally and with a graph database. And so it's Munchkin time. We're going to find the rooms with the best monsters. We're going to find the rooms with the best treasure. So let's try and farm all the XP first. So if we wanted to find the rooms with the highest level monsters in them, that gave us the most XP, we would use this SQL query. We would select the ID and name of the room and the experience points of the monster in there. And then from the two tables, rooms and monsters, we would join on those IDs on that foreign key. And then we go ahead and order them descending so that the highest XP level would show up at the top of the list. We want to get the big monster first. Go big or go home, right? And so that's what this query would look like for a relational database. For a graph database, we would do a match that shows that entire relationship. We want to say match rooms that contain monsters. And it would walk the entire graph and find every match to that pattern in the graph and return all of the rooms that contain monsters. And then we could assign these to variables, and we can return just those individual values, return the ID, return the name, return the experience points. And again, we can order them in the same way. And so this will give us a list of all the rooms sorted by biggest monster to smallest monster. So farm all the XP with graph. Same thing for getting all the gold. We do a join between rooms and treasures. order it descending. And for graph, we end up with a very similar query. Instead of finding rooms with monsters, we find rooms with treasure. And then we return the values we care about in an order that makes sense. Now, these matches can be more complex than just room contains treasure. Like, you can create a match that has a room that contains treasure and contains a monster by having an arrow going to the left in the other direction and then having a monster on there. And so you could say, give me all rooms that have treasure and monsters. And so these matches can get more sophisticated.
Guy, why would you, I'm just wondering, why would you want to return the ID in the name of the room if you're only concerned with the treasure?
In this case, it's I want to find the room that, I want to know the room that has the most treasure. So that I can go to it and take it. Yeah. That's the whole motivation there.
Yeah, I never played this game, so.
Oh, yeah.
Yeah.
I think in general, you probably want to go to the rooms with the most treasure in life too.
Yeah, I mean, that's kind of how video games work too. It's like, well, I could go here or I could go here and get all the gold and buy the equipment so I can defeat all the other monsters more easily. But yeah, so really what this is showing is how you do a join in graph, right?
Gotcha.
How many records do you get back if a room has multiple treasure?
You're going to get, the room's going to come back twice. So if the room has 2 treasure, the room will come back twice. And obviously each treasure would come back once. In theory, you can build a graph where the treasure would be in 2 rooms, which doesn't make any sense in reality land. But but in graph, you could do that. And then so if you have a many-to-many relationship in your graph database, it's going to return all the permutations of that many-to-many.
Are we going to have any demo for this?
I am. I will demo this. So,
Okay.
Right now, we're kind of at the so far so good so what point, right? It's like I haven't done anything with a graph database that I can't do with a relational database. So what's the big deal? Well, there's one thing that you can do with a graph really well that's hard to do in a relational database, and that's having rooms connect to rooms. It's finding paths through that. You can certainly create this structure in a relational database, but querying it is difficult. And so if we want to have our rooms connected to each other, we can do that with graph, and we can do that with relational database. With a relational database, we have to create a brand new table because we're creating a self-referential many-to-many. The room leads to multiple rooms, and every room is led to by multiple rooms. And so you create a new table that's got the from and tos, the connections between the rooms. And then you start inserting rows into that connections table saying room 1 connects to room 2 connects to room 1. And you create, in essence, you're creating the graph of those rooms connections in a tabular format here. And it's just a matter of inserting them. Querying them is hard. Like if I wanted to then find out, okay, so what's the path from the statue room to the armory? Then I have to do joins in complex ways and at arbitrary distances. And so that gets hard. That turns into code and not query. And so it gets into the hairy, weird cases of relational databases. But connecting them isn't hard necessarily. You do have an extra table here, and it's a little counterintuitive. It's hard to think about, but it works. Connecting a room in a graph database is actually the same thing as all the other connections we've done. So here we're matching 2 rooms, and then we're creating a leads to relationship between them. So connecting a room to another room is no different than putting a treasure in a room or putting a monster in a room. It's just connecting a node in the graph to a node in the graph, which is what we've been doing all along. So here we're matching room 1 and room 2, and then we create that relationship between them. And so here's our relational database so far. And you can see we've got that connections table. It's getting a little complicated. Here's our graph database so far. I mean, it's increasing in complexity, but it actually, when I built this map, I actually put these rooms over rooms that are on the dungeon. And so it is actually kind of looking like the two-dimensional representation of this dungeon. And with that graph database, we can start doing some interesting queries that we really can't do effectively in SQL. And it's super Munchkin time. We're going to find the paths to the rooms that have the treasure and the monsters. So here is one query that's a matcher that's interesting. It's got this asterisk here, right? So we're matching two rooms, and this asterisk says match multiple leads to relationships. Hop, find a path. So instead of just matching a room that leads to a room, this also matches a room that leads to a room that leads to a room, or a room that leads to a room that leads to a room that leads to a room, and so on, and so on. And it matches an arbitrarily long number of paths through the graph. And so it will walk the entire graph and find all the paths of room leading to room. And the first thing, if you're astute, that you may have thought of is that how does it know when to stop? Right? If your graph has a loop in it, it could just keep going forever, right? There's an infinite number of paths through it. And the answer is it does. It will not give you, you won't break your database by making this query. It will find that cyclical part of the graph and not return it. And so you'll get all the paths, and once they start folding back on themselves, it'll stop returning results. But this little star gives us multiples. And we can tweak the numbers in there. We can give it a minimum and a maximum number of hops. So do only one leads to relationship, do up to 3 leads to relationships. And so you can tweak your hops, and so you don't, because something that's finding all the permutations of a path through a graph could be a very long-running query if you've got a lot of nodes. And so by reducing the scope, you can improve the performance. So this is an important thing to know how to do. And with that, we can do interesting queries like find nearby rooms. Here, I want to find all the rooms that are close to room number 1. And I use a leads to 1 or 2. And that will return all the rooms that are within 1 or 2 hops of me. That's kind of an interesting query. Find nearby rooms with gold. So there's a more complex match here. Give me rooms that are from my current room, room 1, room ID 1, leads to 1 or 2 hops away, another room, and only give me the rooms that contain treasure. Well, that's kind of neat. That'll give me a list of all the rooms near me that have treasure. I can return the ID and the name of the room and the gold piece value, order it descending, and limit it to 1. And then I'm like, I'm going to this room next. And then I can run it again and go to the next room and the next room and find all the valuable rooms. Slowly work my way through the most valuable rooms in the dungeon.
What's the order of operations with that, since it's 1 or 2? Like, if there's no treasure in a room, does it count that as a hop?
If there's no treasure in the room, then it won't match the pattern.
Okay.
And so it won't come back. If there's no treasure in the dungeon, this match would return nothing.
Okay, gotcha.
It's like in relational databases, you have inner joins. It's kind of the same idea. You could also query the longest path through the dungeon. There's a little bit of extra syntax here I haven't talked about yet. Here we got rooms, leads to rooms, match all the rooms and paths to all the other rooms. So give me all the paths. And then we can assign that to a variable and then ask questions of it. And so here we're saying, give me all the nodes that were in that path. Give me the length of that path. And so this will match all of the paths from room to room in the graph, and then give you all the nodes in each of those paths and the length of each of those paths. And then we can order that by length descending, which would put the longest path at the top of the list. And then if we limit 1, that will give us the longest path through the dungeon that hits all the rooms. So
that would only return the length, right? The number of nodes. It doesn't return the actual path. Is that correct?
No, it actually does return it, because in the return here, we're returning the nodes P, and that will give us a list of all the nodes that make up the path.
Okay.
But
you can actually return relationships in that path as well. I'm just not in this query.
So that's only, if there are multiple paths, inside of each row that would be returned would be going 1 to 2 to 3, and then 1 to 2 to 3 to 4. Would that be?
Yeah, there would, and it would also return ones that feed back on themselves if that's a unique path. So if like you need to go to 1 to 2 to 3 to 4, but you could also go from 1 to 2 to 5 to 4.
Right,
both
right.
of those
So,
would be returned.
yes. Yeah, mine was a subset. That's right. Yeah. So yeah, I got it.
Yeah, and so it's just matching that pattern everywhere it can in the graph.
But it's actually returning multiple things with each row, if you want to consider a row, if that's the proper notation.
Yeah, it's we're well past rows now. Now, I mean, I remember returning this as tabular data, right?
Right, but it's a group of data per result.
Yeah. I mean, it's the results are tabular, but the queries aren't.
Right.
And then I'm using an order by and a limit to get the longest path.
Right.
Here we have the room with the biggest treasure. Here we'll match max : treasure. So this matches all treasure, assigns you the variable max, and then we can say with max as an aggregating function and assign it to a variable to use later in our queries. So we can query the graph and grab a value out of it. We can get the average or the max, or there's a lot of aggregation things here. Then we can match all the rooms that contain treasures and filter them by ones where the gold piece value is max, and then return those. Technically, if there's a tie for first place, this query will return more than one result. But using that with statement, we can sort of query our graph before we query our graph, if that makes sense. Lets us pull a value out of it that we can then use later. And then, of course, the path to all the gold is putting all these queries together. Here we're using that max treasure variable assignment, where we're saying match max treasure. We get that the room with the maximum value. Then we do a match of room that contains a treasure where that max value is true, and we assign its ID as the destination. So now we got now we're using we have a destination ID. And then we can get the path from the room we're in, room 1, where start 1, leads to stop room, where stop is destination ID. And then we can find all the paths between the start room and the stop room, and then get the nodes and the length, and then order and sort, or order and limit. And that'll tell us the path to the shortest path to the most gold. So it's a rich query language, and there's more to it than this. This is just sort of this is the most advanced query in my talk here. I'm going to show that this is real and do a demo here. And I've got about 6 minutes, so I want to make sure I get my demo in because I've been a little long-winded. And so I've written a JavaScript dungeon generator. And I'm not going to go into the code too much. I'm going to show you the code that actually does the graph execute here. So here we call, say, execute and return a single value. Execute, I've got a graph client from Redis. I pass in a query, I pass in parameters. And that's going to return results, which I can then walk through. But the key thing here is this query. In my queries that I'm using here.
Hey, Dad. Are you on your way?
So,
okay.
Hey, Meg, you're not muted. Sorry. So here we got our little thing that calls that graph.execute. And so we can give it a query. Here's our match dungeon where ID of the dungeon is equal to dungeon ID, and match room where ID of the room is equal to the dungeon room. And then we can create has an entrance. And then these little dollar signs are replaceable values. So we pass in our query, and we pass in a JSON object that allows us to, or a JavaScript object that allows us to fill in those missing values. So that's how that works at a code level. But I'm going to go ahead and run this thing. And then I'm going to use Redis Insights, which has got a nice little graph querying tool built into it. And so I can say match, say n, return n. This will match everything in the graph. That's all the treasures, the monsters, the rooms, the dungeon itself. I think this is the dungeon, yeah. And then you can see that this room is called the Shattered Delve of Tel Wold. I guess that's how we'd say that. And if I double click it, it'll highlight it. We can match specific things here. So we can say match D, return dungeon. That'll match just the dungeon. And so that's the shattered delve there. If I regenerate my dungeon here, just to show you that my code is real, I've regenerated the dungeon nice and fast. I rerun the query. And now we see it's the lonely castle of Minifer. And the nice thing with Redis graph, or the Redis insight is that we can actually walk the graph here. Here's the entrances and exits to our dungeon. Here's the dusty jail. The dusty jail leads to places. It looks like it doesn't have any. Let's go to the black jail. I'm not finding anything that has treasure. But this is kind of a, I mean, honestly, this is kind of sexy. It's just kind of cool the way it works, right? And I'm having trouble finding treasure. So maybe what I need to do is use a better query. So here we've got some of these queries, like if we want to match all the rooms or the monsters or the treasures, like let's match all the rooms. If I do a query that returns tabular data with this, I do not get the pretty graph. Instead, I get a list of all the rooms. So that's all the rooms in this dungeon. This dungeon doesn't have very many rooms this time. If I want to get the rooms and the treasures, then there we go. So that gives us a list of all the rooms and treasures. If I actually want the nodes instead, then I can get back a graph showing the rooms that have treasure. Here we got a sack of coins worth 1,000 gold. Here we have 2 gems. Here we have the chalice of Rushudo. It's totally randomly generated names too. Some of the monsters are fun too. Let's see if we can get all the monsters. Yeah, so some of them get unique names. Brazuk, the Zorn, Goran, the Atten. Sometimes it's like there's 3 Attens there, right? So, yeah, it's a nice, fun little dungeon generator. The code of that is all out on GitHub to play with. I'm going to do the shortest. Let's do the find the longest path. I think that's a good one. Actually, no. Let's do the shortest path to the most gold. Now, this is a monster of a query to type, which is why I'm totally copying and pasting it. But when we run it, there we go. That's the shortest path. And if we look at in a tabular sense, we've got 3 nodes. And there's the IDs of those nodes, 1, 4, and 2. That's the order they're in. If we go back to the graph here and we double click on the black bridge, we'll see that the black bridge is at the entrance or the exit there. Anyhow. Yeah, so the abandoned chasm is the entrance to the lonely castle of Minifer. So these, it's a real database. You see the queries come back pretty well. Now, admittedly, I have a really beefy MacBook Pro. I had a little tiny like MacBook Air, and they wouldn't run. But on my nice beefy MacBook Pro that I have now, they work great. So
that's stuff that would work on a server anyway, right? That's a server-based thing that you typically.
Oh yeah, absolutely. Yeah. So practical applications, social networks are an obvious one. I follow someone else on Twitter. I like their tweet. These are all relationships. Genealogy, which is really just social networking over time with people who are related. So-and-so begat so-and-so, begat so-and-so. This person married this person. These are the same sorts of relationships. Transportation networks I touched on earlier. Logistics is another good one. You could trace like the paths through a system that products take to get to market. And then if there's problems, you can troubleshoot them that way. Here's some list of resources. Redis graph, of course, is at redisgraph.io. And all these links are in the slides that will be updated on my website right after this talk. I work at Redis. Go check out our Discord server. I know I said that in my last talk too, but I'm there. I'm always happy to answer questions. It's discord.gg/Redis. We've got free courses on Redis University, just on Redis stuff. And if you want to get a free server-based version of this to play with, Redis Enterprise Cloud, Redis Cloud Essentials, it's got a free 30 megabyte database that you can play with. and do some graph stuff with in case you don't have a PC that can handle it. Here's the link, and I'll post this in the chat as well. And that's my talk. So thanks a lot. I don't have time for any questions. I went over by 2 minutes. I'm sorry to the next person. Let me go ahead and get that.
Person?
We're done for the day.
Oh, I'm the end? Well, here
You
then.
are the be-all, end-all.
Okay. And here.
Yeah, can I ask you a question now that?
Yeah, sure, absolutely.
So during your talk, you had alluded to that it's very tempting to do, object inheritance type of graphs, if you will.
Yeah.
Would relationships be best expressed with an is-a or has-a kind of thing? Would that be a valid graph? An employee is a person, is you can have that kind of chain built?
You can totally do that. I haven't really explored the ramifications of that. But I mean, if you think about your code is a graph, right? I mean, you got your memory and your code in memory, we call it an object graph. And so that's having the has a relationship between your different objects in memory. And, your type system is a relationship, and you could represent them in the same graph. That would totally work. And, I mean, that is kind of what your code is. I don't know if there's value in doing that in a graph database or not. I think you have the same caveat, which is composition over inheritance. Right? I suspect that's true in graph as well, but there's no reason you couldn't do that.
Super interesting. Thank you.
Yeah, it is. That's a neat thought. I haven't really thought about that actually, so I appreciate you asking that question. And any other questions?
Yeah, when you were running your queries, you were running the queries against the graph. How would you do it relative to a point? What's the shortest distance, the most gold from where I am, and specify that?
Well, you'd have to know where you're at. I put the at after there because I'm a Midwesterner. But you'd have to know where you are, right? And in my queries, I actually did that, right? If I go back to animations are slow. But anyhow, in my queries there, I specifically would query and say, just I'd use a where, or I'd use the curly braces to say match a room that has an ID of this to represent my start location. And so I would know what room I'm in already. Now I could find that out by querying the graph if I had some information about the room or about the node. It's well, I want to, starting from the node that has this property, then, find a node that has this other property. But you have to be able to have some way to identify the beginning and the end. You could query the whole graph for just all rooms leading to all rooms and then walk that information. But that would, well, then you're not really using a graph query. You're just bringing all the nodes back and walking it yourself. So, any other questions?
I actually have a question. When it comes to one-to-many or many-to-many relationships, can you define those using wildcards, or is there some other syntax? And I posted an example in the comments.
Oh yeah, okay. So you got an NPC that is hostile. So like an NPC that has a. Oh, so you So we want to find. You want to filter out. I'm trying to parse your query here. You're trying to parse a many-to-many relationship where you've got, like say, give me a concrete example here.
Okay, so generally monsters are hostile to NPCs. So I would say I have an NPC. I want this NPC to have a hostility relationship to all monsters, as opposed to defining that individual curve.
Okay, so you could have one thing you could do is you could have multiple labels where you could give it a label of is hostile and a label of monster and a label of NPC, and then you could in that case you could just find everything as hostile.
Okay, but I couldn't select the entire monster category, for example.
Yeah, there's probably ways to do that that I'm not sure about. The Cypher query language is really thorough. And it's got a lot of capabilities, but you don't actually, like if you wanted to, is hostile could be an attribute on a node. And then you could just select all nodes that are hostile regardless of type. Yeah, like in the query that I did here, where I say, I can say match n. I am querying all nodes regardless of their label. And so that just gives me all the nodes in the graph. I could match a node that has a property of a name and then give it a name like that as well. I'm trying to think of, see if I can find something that has a name that's interesting. We'll call it 3Ns. And so that's going to return a node that matches that property without asking what the label is. So the labels are optional in the query.
Okay. Well, thanks for going into that.
Oh, no problem. So it's the Cypher query language is pretty. It's got a lot in it. Redis doesn't fully support the entire breadth of Cypher yet. We're adding capabilities as we go. We just recently added the ability to do sort of the equivalent of an outer join, where you can say match this thing always, and then bring in this if it exists or not. So you could get all the rooms and their treasure, even if they're, but still get a list of all the rooms. And that was just added in the latest release like a week ago. So, so we're taking Redis Graph and expanding it. Other graph databases have that capability already. Others don't. It just depends on the graph database. And not all graph databases use Cypher. So,
Guy, what are the other languages that are typically bigger languages besides Cypher? Are there other big ones?
Cypher is the big one that I'm aware of. I haven't looked into the rest of them yet, honestly. I mean, I'm a little bit narrow in that I've looked at Cypher because it's the one that my company's product uses.
Okay.
And I just haven't, and so I have to be kind of broad. And so I don't have a lot of I have this problem where I'm a little bit of a jack of all trades, master of none. And but they're oftentimes better than master of one. That's the full poem.
Well, I know there's Gremlin, but that's the only other one I know that can traverse graphs, and that one's a different implementation behind the scenes as well.
Yeah. Well, and the Cypher stuff has been open sourced by Neo4j. I know a lot of people have been talking about Cosmo lately.
That one's just in Gremlin. Yeah.
Is it using Gremlin?
Yeah.
Okay. Well, so now I know. Thank you. Cool. Well, are there any other questions? I mean, I'm fine to answer more questions, but Bill may want to go about his day. I don't know.
I have no life.
Bill, I was about to say you have no life, but I was like, I've been nice all day, so I was thinking it though.
Well, we found Ghe extremely entertaining today. That was a good way to end, but it is probably time we shut all this down. Thank everybody for attending, and of course, thanking all the speakers for putting in time. And but I do like the Redis talks. It was refreshing to see how to do interesting things like find aliens and monsters.
Well, I mean, it's important, right? I mean, the best campaigns for D&D are the ones that have both of those elements.
Mm-hmm.
It's also important to note that Bill is extremely loud, even virtually.
That's my fancy blue microphone. So
yeah, I have that one too. Wait till you meet me in person.
I have the Yeti, which is the little version.
Yeah, that's the one I have too. The blue Yeti.
Yep.
We need a woohoo or two.
I think we do. Can we all do woohoos? Prizes. The only prize they get this time is all the good sessions. So, woohoo to you too.
Woohoo.
Well, I'm just glad that everyone attended my talk. So thanks for attending.